Good day to all. Today we can study about the RC phase shift oscillator and the subject analog circuits. So an RC phase shift oscillator using a BJT generates a sinusoidal wave by combining a BJT amplifier, that is common emitter amplifier, for 180-degree phase shift. So the first diagram represents the 180-degree shift common emitter amplifier, and followed by a, three-stage RC ladder network, each providing 60-degree phase shift for a total of 360-degree loop phase shift, satisfying the Barkhausen criteria. So this particular circuit operation we are going to discuss. So that combining the above two, this is the structure of the RC phase shift oscillator. First stage having a common emitter amplifier, and the second stage followed by 3 RC ladder network. So this 180-degree from BJT and 180-degree from RC network sum to 360-degree, ensuring positive feedback for sustained oscillation. So RC phase shift oscillators uses a common emitter single stage amplifier phase shifting and phase shift network consisting of three RC sections. The output of the last section must be returned to the input. So the output of the last section, that is C, is given as feedback to the input through a resistance R3. So with the input impedance here HIE, it should be actually mentioned as R3 equal to R minus HIE, where HIE is the input impedance of the circuit. This is the same considerations while choosing this R3 value. So neglecting R1 and R2 as these are sufficient large, we can write HIE as input impedance of the amplifier stage R equal to HIE plus R3. So R3 equal to HIE minus R. And the phase shift given by each RC section is tan inverse 1 by omega CR. But because R equal to 0 is impracticable, because R is made 0, the phi will become 90-degree. But making R 0 is impracticable, because if R is 0, then the voltage across it will be 0. Therefore, in practice, the value of R is adjusted to get the phase shift of 60-degree. This is the reason why we are using R3 RC networks. So if the values of an RC and C has chosen that for the given frequency, totally each should be, so the R value should be unique, and it should be having very much important to take care of that. It will be giving a total phase shift of 180-degree between its input and output voltages. So which satisfies the Barkhausen condition. So we need to calculate the frequency of oscillation for this RC phase shift oscillator. So consider the circuit ignoring the R1, R2. Draw the small signal AC equivalent circuit. Will be having in the base side you have the HIE. That HIE is added with R3. So totally it will be having a HFEIB, the current source, by drawing the small signal AC equivalent circuit, and HIE, RC, RR. And we are going to consider this HIE into R3 as total value of R. And we are going to replace this current source to be a equivalent voltage source. So HFEIB into RC, we are going to convert this parallel circuit. So here we have a parallel circuit that will be converted to a series form, that is HFEIB RC as the voltage source, and RC is equal to K into R. So by assuming that, so we are replacing the current source HFIP by its equal voltage source, assuming the resistance RC to R to be the K value. Now apply KVL to all the loops. So in each loop apply KVL. So for the loop 1, first loop, this is the loop 1. If you are applying KCL, you will be having I1 into R, I1 into RC, then minus 1 by j omega c into I1, then minus I1 into R, and then here minus HFE into IB RC. So combine the like I1 parameter, I2 parameter, and I3 actually. But we here first loop equation, we don't have the I3 term, which is treated to be a constant term here. Now, second loop equation, you are going to apply second loop equation. We don't have any voltage source. So, minus 1 by j omega c I2 minus 1 I2R, and this is common, right? I2, the current flow through this is I2 minus I3. So, it should be minus I2R plus I3R. Then here also the current flow will be I2 minus I1. So, minus I2R, and here it is plus I1R equal to 0 combined in terms of I1, I2, I3. So we have I1 term, I2 term, and I3 term. Similarly, apply KVL for loop 3. For loop 3, if you are applying this, here also you don't have any voltage source. So minus 1 by j omega c I3. Here the current is I3 minus I2. So it is minus I3R minus plus I2R, and you have one R value here. So minus I3R. So totally it becomes minus R into I2 plus 2R plus 1 by j omega c I3. We don't have any I1 term here. To next form that is a determinant. So this is the determinant formed from this all the three equations. Considering the coefficients, you are going to form it as a determinant. And in this determinant, you are going to expand the determinant. So for the first, we are going to consider this means R plus RC plus 1 by j omega c into 2R plus 1 by j omega c into 2R plus 1 by j omega c minus R square. So, and expand this, you will be getting this equation. So, R plus RC 1 by j omega, and we are going to be getting a expanded form here. And after that expansion, you are going to simplify this. And what is the thing is, you need to separate the real parts and the imaginary parts. So, rearranging all the equations, first you are going to simplify it. So, for 2R in this term as a plus jb the whole square. And here multiply it and bring this as r minus r square here. This is minus r square. The next term, then this term. So it is expanded as a plus b the whole square. A plus b the whole square. So that is the second part of equation here. Next, after that, separate the real part, and you want to separate it as a real part and imaginary part. Because we need to find the frequency of oscillation and the condition for oscillation. So first you are going to expand the equation to find the frequency of oscillation, equate the imaginary part to 0. So you have the imaginary part to be here one term, here the other term, the imaginary part. Then here you have one imaginary part. So take the terms alone will be equivalent to 0, and uh, equivalent to 0, and just simplify it, you will be getting 1 by omega square c square is equal to 6 r square plus 4 r rc. We need to use this equation for the subsequent derivation. So keep it as another one equation number. So now from this, can you find the frequency of this oscillation using this f square? So using this f square, that is omega square, and bring the other terms towards one side, and apply for this RC by R here. If you're taking R square outside, here it becomes RC by R. This RC by R is nothing but K. So your frequency of oscillation will be equivalent to 1 by 2 pi RC root of 6 plus 4K. Next is to find your condition for oscillation. For that, equate the real part to 0. So in this equation, you need to have this real part. This is your real part. Then this is your real part. This is your real part. Remaining terms are the imaginary parts. So take that alone to be equivalent to 0. So you'll be getting that a real part will be equivalent to 0. And here in this 1 by omega square c square, you want to replace this by your frequency term later. So first you expand this, expand it and simplify it. We need to find the condition for oscillation. That means HFE we need to find. Remaining all terms you can. So 1 by 1 from 1 by omega square c square, you are going to substitute over here. So if you are substituting over here, you will be getting this 6 r square plus 4 rcr. expand all the terms one by one, expand and remove all the bracket terms and simplify it. You will be getting an equation like this. Here, you bring the HFE term towards one side, remaining terms to the other side, and you will be getting HFE equal to 29 R by RC plus 20. Now you can replace this R by RC as RC by RSK. So this RC by R is R by RC is 1 by K and RC by R is K. Now we will be getting the HF. This is the condition for your oscillation. So use equating the real part. We have found out the condition for oscillation. Equating the imaginary part, we have found out the frequency of oscillation. So where K equal to RC by R. So we need to find the minimum value. For that, you have to take this dou HFE by dou K as 0. You'll be getting the K square value so that we can find the K value also. So now substituting this K value, what is your minimum HFE you have obtained is 44.54. That is the minimum value of HFE for your sustained oscillation. This is obtained by applying the maxima minima concept. So here we need to find the minimum value. So we have applied the minimum value concept, that is dou HFE by dou K is equal to 0. You have obtained the K value. Once you have obtained the K value, substitute the K value in HFE and you have found out the minimum value. So advantages are simple design or on the oscillations of this low frequency range, that is audio frequency range, is as it is an oscillator with the R and C component, it is a low frequency. So fixed frequency oscillator produce a sinusoidal waveform. But the thing is, disadvantage is, now we have three RC sections, right? So it will be considered as, for a fixed frequency oscillator, it has to satisfy the condition, means somewhat it is physically, practically impossible, and the frequency stability is poor due to the change in the value of components due to the effect of temperature, aging, and other environmental conditions. So this is about the RC phase shift oscillator. So it is having two sections to in order to satisfy the Gaussian criteria condition. First, you have a common emitter amplifier with 180-degree phase shift and another three RC sections with 180-degree, forming a 180-degree phase shift. Each section will be having a 60-degree phase shift. And after that, we also after that we have solved for taking the loop, applying the loop condition equations for all the three loops, and you have obtained the condition for oscillation and the frequency of oscillation. Then the minimum frequency, the condition, minimum value of HFE also we have obtained. So hope you have understand this. Thank you.